Okay, welcome back, and let's continue on with VSEPR theory. So, an unshared pair of electrons would be important in projecting shapes of molecules because it will occupy one of the points of that tetrahedron shape we were talking about. However, it is not an actual atom, so it would not be part of the molecular geometry, but it would be a part of its electronic behavior. And unshared pairs are different than bonded pairs in a very important way. Bonding atoms pull those electrons a little bit further away from that central atom. The unshared pair, however, strongly repels those bonding pairs because it's held very tightly to the nitrogen nucleus. Therefore, the measured bond angles for the hydrogen-nitrogen to hydrogen bond angle is less than 109.5. It's actually 107. You don't have to know the numbers, though. But you should know that it's smaller. When we go on to a water molecules, the oxygen has 2 lone pairs on it, which occupy 2 points of our tetrahedron. However, now those 2 pairs are pushing that bond angle even smaller, and it becomes 105 degrees, and the molecular geometry of it would be flat, but bent, and so we call it bent instead of flat or planar. Carbon dioxide, the central molecule, has no lone pairs on it. The oxygen atoms each have 2 lone pairs, but we end up with a linear geometry. Those bond angles are 180 degrees between oxygen, carbon to oxygen, and it is a straight line for all 3 atoms. Here you see I've marked out 3 of the shapes on this slide. I do want you to know linear, trigonal planar, bent, pyramidal, and tetrahedral. You might want to pause and make note of that. What causes valence shell electron pairs to stay as far apart as possible? Well, electrons are negative. They don't want to be near other negative things, and so they push as far apart as they can. Hybrid orbitals. Hybrid orbitals are where we take S and P and we start blending them. We'll do some discussion of these in class. But what is a hybrid orbital? VSEPR theory works pretty well when accounting for molecular shape, but it does not help describe the type of bonds that are being formed. Hybrid orbitals provide information about both molecular bonding and molecular shape. In hybridization, several atomic orbitals mix, blend, average, and form a new type of orbital that's called a hybrid orbital. And all of the ones that are mixed or blended together are equivalent. And this is important because the bond angles and the bond lengths then would all be the same in, say, something like CH4, methane. So carbon has 2 s orbitals and 2 p orbitals, and when we hybridize them in methane, we blend all 4 of those together, and we end up with an sp3 hybridized molecule. So, when 2s orbital and 3 2p orbitals, 4 total orbitals, blend or mix together, we get an sp3 hybridized orbital with a tetrahedral bond angle of 109.5. So, here we see the 4 orbitals for hydrogen are denoted in yellow. The hybridized orbitals for carbon are denoted in green. And we form 4 sigma bonds. I do want you to be able to tell me how many sigma bonds a molecule has. The extent of overlap is unusually strong in these covalent bonds. Ethene, which we have a carbon-carbon double bond, now we have a different type of orbital hybridized because one of our p orbitals will remain unhybridized and 2 p orbitals and the sigma orbital will hybridize, or the s orbital will hybridize to give us 2s and 2p,
and we end up with sp2, and then we have a bond angle of 180 degrees. So here we see the p orbital that is in blue. The green ones are hybridized orbitals, our two s orbitals on each side for our hydrogens. And so we've made a sigma bond between carbon and hydrogen, a sigma bond between the two carbons, but then we've also made a pi bond between the two carbons as well. And remember, a pi bond has both kind of a top and a bottom, or two pieces make up one pi bond. So in ethene molecules, the 2sp hybridized orbitals from each carbon form a sigma bond with the molecular orbitals of the 4 available hydrogens and with each other. And that gives us the 1p orbital left over, which will then form a pi bond between the two carbon atoms. And as you can imagine, ethine would be a little more difficult because now we're going to have 2 pi bonds and one sigma bond between the carbons, and then a sigma bond to each hydrogen from the carbons. So if we look at it here, we see that we have 2 p orbitals. One would be the top one and the bottom one. The other one would be the back one and the front one, that are going to form pi bond in the front and back, and pi bond on the top and bottom. There's still a sigma bond between the two carbon atoms. You have to have a sigma bond. And then there's a sigma bond between carbon and hydrogen. So this bond length would be even shorter, and it is not as strong as the sigma bonds. I can break pi bonds relatively easily, and the sigma bond is really hard to break between carbon and carbon, or carbon and hydrogen. So, how many hybridized orbitals? When you have 1 2s orbital is hybridized with 3 2p orbitals, that should be sp3. So this superscript tells me how many p orbitals are being hybridized. Key concepts, finally. Just as an atomic orbital belongs to a particular atom, a molecular orbital belongs to a molecule as a whole. In general, in order to explain the three-dimensional shape of molecules, scientists use the valence shell electron pair repulsion theory. Orbital hybridization provides information about both molecular bonding and molecular shape. And here are your vocab words for this section. The big idea. Shared electrons and valence electrons that are not shared will affect the shape of the compound, the molecule, as the valence shell electrons stay as far apart as they possibly can. There we go. End. Hallelujah. I will see you in class. Bye.